Good. So it's my pleasure to have Wolfgang Gregor Hollik here with us. He is now in his second postdoc in Karlsruhe before his first postdoc at DESY. And he will talk about a work that he did over the last years, which culminated in at least one publication, which he's indicating here, on vacuum stability in supersymmetric models. Wolfgang, please go ahead.
Okay, thanks a lot, Sven, for the introduction. And for me, it's also a pleasure, of course, to be virtually here in Madrid to give the seminar also.
I can assure you, if you had been able to come, we would treat you very well, and we would go for a nice tapas tonight.
Exactly. But, this is really what I'm missing and what I'm a bit sad of. But
yes,
due to the current situation, let's do it like this, and maybe soon we can meet in person again. And so the work I'm going to talk about is not only this one publication, which is the last one, joint publication with Georg and Jonas, but this is also based on some previous paper I had with myself. And this is basically the first part I'm going to talk a bit about to motivate then this bit more detailed analysis we did in this paper from last year. Okay, so now okay. So I'm going to talk about vacuum stability, and here I want to chart the vacuum landscape in SUSY benchmark scenarios. This is basically what we did in this work. And first of all, I want to give a brief introduction to vacuum stability and what is the difference in extensions of the standard model compared to the standard model. So as we all know, the electroweak standard model, we have this very simple Higgs potential, which has a bilinear and a quadrilinear term, or a basically quadratic and quartic term. And for large field values, you can forget more or less about this, the first term that is responsible for the electroweak symmetry breaking, and you are left only with this quartic term and the self-coupling lambda. Now, including loop effects, the running of lambda will lead to a point when you now basically go with a scale that is related to the field strength of the Higgs field. You will soon, not really soon, at rather large values of the scale, you will reach a point where lambda turns towards 0 and gets actually negative again. And then a new minimum is developed well beyond the Planck scale. So this is basically the instability we are facing in the standard model, and then you can go to this discussion of metastability, discuss the vacuum lifetime, and so on. This is the case in the standard model. In supersymmetric models, the situation is a bit less simple, and we are not going to find new minima beyond the Planck scale, but already at around the corner of the SUSY scale. The reason here is, so here I printed parts of the scalar potential in the MSSM, especially the soft breaking terms, those terms that break supersymmetry softly. They will be responsible for driving new vacuum expectation values of all these new scalar fields around. So in the MSSM, we have, of course, two Higgs doublets. We have also the scalar partners of the top and bottom quarks in this case as printed here, and they have this soft breaking masses, and they have this trilinear terms that will be at the end responsible for driving new vacua related to vacuum expectation values of this quark fields, and these will be named then charge and color breaking vacua, since here you break color charge as well as electric charge. So as I said, the minimal supersymmetric standard model is a multiscalar theory. Besides these two Higgs doublets, we have, of course, a lot of scalar quarks, scalar leptons. So at the end, there are 12 colored and 20 charged directions compared to the one neutral field direction we have in the standard model. However, the charged Higgs directions have been found and proven to be safe in this type 2 Higgs doublet model, as we have in the MSSM. This has been proven in the 90s. And the standard model Higgs potential is, of course, quite simple. Since we have this SO4 symmetry, at the end, it reduces to a one field potential that has to be minimized. This you can do. You find the vacuum expectation value, and then of course you can include this quantum effects, this running of the self-coupling, which in the MSSM is of quite a different characteristic when you really include now this new degrees of freedom you have. So all these new scalar quarks, leptons, in principle, they can also acquire vacuum expectation values. Let's say the partners of the top and bottom quark, they are coupling with large couplings. The Yukawa coupling of the top quark is, of course, 1. The Yukawa coupling of the bottom quark can also be enhanced due to the SUSY threshold correction. Additionally, we need...
Sorry, Wolfgang,
yeah?
You seem to be touching the microphone or so. There's a strange sound, or I don't know. There's
okay, then I try not to move much.
Thanks.
And especially in the MSSM, basically to reach towards this large value of the Higgs mass of 125, you also need a large stop contribution, which is related to this trilinear coupling that will at the end drive this charge and color breaking vacuum. And at the end, basically we will talk about constraints on these parameters, either xt or at. I mean, they are related, as you all may know. I'm also showing this in more detail later. And at the end, I mean, the main goal is to get reasonable constraints on these parameters from the lifetime of the electroweak vacuum, or even from stable vacuum stability, metastability analysis. So the question is there an analytic solution? Of course, it's not really possible, but you can try it approximative. You can also try it numerically. So now first, I'm going to outline a bit how you can try to boil down from this rather complicated object, where this is only a part of the scalar potential in the MSSM, how you can derive some semi-analytical bounds. So here I printed the Higgs stop-spotting potential. So we have the neutral components of these two Higgs doublets, H1 and H2. We have the scalar partners of the top quarks and the scalar partners of the bottom quarks, and of course they are left and right-handed quarks. So we have also partners of the left and right-handed fields that are indicated here with the indices L and R. We have the soft breaking masses for the doublet. We have soft breaking masses for the right-handed fields. We have this mu times Yukawa type coupling, which is a trilinear coupling similar to the A term. However, here you are coupling to the basically to the opposite Higgs doublet, where here you couple the top quarks to the up type Higgs. There you via this mu Yukawa, you couple the top quarks to the down type Higgs. And maybe people who are working in the MSSM without considering vacuum stability there might be a bit confused why here is no tangent beta or cotangent beta. This is exactly hidden in the field. So we are now considering the fields as dynamical degrees of freedom, and we are explicitly not sitting in the electroweak vacuum. At the end, the electroweak vacuum will be one of many solutions when you look for stationary points of the sky. There are here coming the D terms. They can be, of course, also quite large. And now what has been done already many years ago is to go into a so-called flat direction. So basically, you want to reduce the amount of the quartic quadrilinear couplings by choosing certain directions in the field space. And here, for example, if we choose the left-handed stop field direction, the right-handed stop field direction equal, and the same for the bottom quarks, you will see that this D term related to the strong coupling vanishes. So if we do this now, already the whole object seems to get a bit simpler. Now we can look into the other D terms related to the hypercharge and the weak isospin. You do a similar identification of the fields. Like here you say, okay, the top quark field goes in the same direction as the up-type Higgs, which somehow also seems to make a bit sense. The bottom quark goes in the direction of the down-type Higgs. And then now also these fields disappear, and we are left only with a scalar potential of 2 scalar degrees of freedom. They're complex. Now we can go further and simply neglect one direction, and at the end, surprise, surprise, we are left with only a single scalar potential. This is basically behind this very old analytical bounds that are still somehow used to give a quick and dirty estimate whether or not charge and color breaking minima exist. And this is quite simple. So we have this quartic potential, there's a mass term, there's a trilinear term, there's a self-coupling. All these coefficients can be expressed in terms of the fundamental couplings of the theory. Now you minimize this guy. This you can do, I said here in kindergarten, maybe you have to go to school to do it. And at the end, you get a relation for the existence of further non-trivial minima if this A, this trilinear coupling squared, is larger than 4 times m squared times a. Or the other way around, if it's smaller, then you are safe. And this is then encoded in this well-known constraints that have been written down already in the 80s. For AT, for AB related to the soft breaking Higgs masses, to the mu term and the soft breaking squark masses. However, this is in the limiting case here where basically you choose all these field directions to be equal. Now we can, I mean, the next step is to question this and say, basically, what is the mistake when you simply choose a certain field direction? Indeed, this problem is partially solved. However, as I mentioned, it's of course related to this to a certain choice in the parameter space, in the field space that might not be optimal. Then there has been discussed also already in the 90s the issue of stability, instability, metastability that is related to vacuum tunneling. I'm also going to talk about this a bit more in detail later. And some years ago, there has been one computer tool being thrown to the market called Vivacious that attempts to find all tree-level minima of the theory and then also includes one loop corrections that are related to the normal Coleman-Weinberg potential, and then minimizes basically the one loop potential in the vicinity of the tree-level minima. And this uses another code, Cosmo transitions, at the end to calculate this bounce action and the tunneling times. About this,
Wolfgang, we lost your voice. Now, say something.
Now, is it better?
Yeah, now at least we hear you again. Yeah, let's try.
Is it better?
Yes.
Okay.
Yes.
I try to do it then without the headphone. Okay, so here I just show a small cartoon basically to picturize this type of constraints. So in the case a squared is smaller than 4 times m squared, we find the normal, let's call it trivial minimum here at the origin, and the new local minimum deriving at higher field values. Now when these parameters are equal, they are degenerate. And from this point, now you can start discussing the probability of tunneling from this vacuum to the other degenerate one. And in case you are larger with a squared compared to this combination, then you get a new non-trivial minimum at higher field values. And now imagine here at the origin is the well-defined electroweak input value. Now you tune your A parameters in a way that suddenly at larger field values you generate a new vacuum related to top or bottom, stop or bottom webs. You would find at the end either non-vanishing probability to tunnel from this vacuum to the deeper one, or you do a conservative estimate and say, okay, the electroweak vacuum you were starting with is not the true minimum of the theory, it's not the global minimum, not the true vacuum of the theory, so we exclude this point. And this is basically what I'm going to show a bit on the next slide. So here's just, again, this potential from before rewritten a bit, that we now try to capture the missing deviations in this field direction. So now I say I want the top squawk field direction to be somehow aligned with this uptype Higgs, but it can deviate with a parameter alpha. The same is true for the downtype Higgs and of course for the bottom squawk. At the end, you get again a potential one, looks like a one field quartic potential. It has a mass term and a trilinear A term, a self-coupling term. However, these now depend somehow on the configurations among the field space. And you can express them in terms of the fundamental parameters. And now you can try to improve this old A parameter bounds by playing around here with this additional deviations basically from this one field direction where you set all fields exactly equal, by minimizing here, maximizing there, and so on. And then I found some new bounds that, to my knowledge, have not been published in the literature. So one, for example, if you just play the opposite game and set the bottom squawk direction equal to the uptype Higgs and all the rest to 0, then you get a relation between the mass terms here and this mu times bottom Yukawa coupling. And this can be actually quite large when you include this SUSY threshold corrections to the bottom mass. Then this Yukawa coupling can grow. However, you see, of course, it is in the numerator and the denominator. So at the end, there are also some cancellations, and then you can also derive a bit more complicated expression where you have a bit more sophisticated field direction at the end. This is also, again, just a random choice, more or less, and I'm going to show this now on the next slide. So here, the red line is basically corresponds to this lower bound for an optimized value of this alpha. Now, when you go there and you simply do a numerical minimization, look for the deeper minima, you find the blue points that are excluded. So now in this case, when you choose the downtype Higgs direction, in the negative of the square root of the absolute value squared of up and bottom squawk, you find, for example, by just using the simple bound you would exclude too much parameter space. The gray curve corresponds to the other bound that has not been included here in the numeric. So there we only have these fields and this relation that is printed on the bottom part of the slide. Now, if we change the sign here, go to the plus sign, you'll see, now we overestimate a bit the constraint. So the numerical points are not all covered by this. So at the end, what does it tell us? Don't take these analytical bounds too serious, especially in the boundary regions. You have to be a bit more precise. And for this, we started to basically develop a tool that can do all this analysis numerically and also quite fast in a way that you can easily include it in large-scale parameter scales. So let's do it better. Exactly. As I said, one field direction is not enough. One type of WEFs is not enough. So it's completely wrong to say the new Higgs WEFs are exactly the same as discharge and color breaking WEFs. And this is what you do when you restrict yourself in one direction in the field space. The choice of the trilinear couplings, of course, is crucial. And this will be at the end also the interesting parameter plane we are talking about. We are doing it numerically, and of course, don't underestimate the bottom Yukawa corrections. This can be shown here. So this is also from the previous study. Here I give some constraints on AT versus mu. in a certain MSSM parameter configuration. The blue points are all those points where the electroweak minimum is indeed the global minimum of the theory. The light blue part corresponds to a region where we are somehow in the vicinity of the 125 Higgs. So, I mean, this indicates, of course, that you have to go to the larger values of AT to get the Higgs mass, right? The red area is excluded by the existence of stop wefts. The orange part is excluded by the existence of bottom wefts. And in this left corner, simply tachyonic bottom quarks existed in the spectrum. That's why they were excluded and simply left white.
Sorry, you remember the value of MSUSY for this plot?
It was 1 TeV. This is what I'm also going to show on one of the next slides. It was just, I mean, it was just a random study to see basically what type of constraints can you get. One more point here was chosen A bottom to be 0. Now we increase A bottom, and you see that more and more of the parameter space is closed by the existence of bottom wefts. And this made me a bit worried. So, and that's why I wanted to go a bit more into detail. So, as I said here, I used a SUSY mass of 1 TeV, and somehow to get the right Higgs mass, you are in this region where you have to talk about stability, metastability, instability. However, this analysis was only an exclusion from global minima electroweak or not. Nothing about vacuum tunneling. However, as I found for myself in 2016, the MSSM is still alive because, interestingly, or not interestingly, because it's at the end quite obvious, the constraints get weaker with an increasing MSUSY. Crucial is at the end, of course, the ratio of xt over MSUSY, where xt is defined in my setup here, where I didn't factor out the Yukawa couplings from the A terms like this. So it's basically at the end AT minus mu times cotangent beta. And then let's see what is going to happen when we go now to larger SUSY values. So here now I show the values of xt over MSUSY compared to MSUSY from 0 to 5 TeV here for a mu value of 350. To generate this plot, I used Spheno at that time. This dark band that indicates these points are those points that again produce a standard model like Higgs in the vicinity of 125. I think in a 2 GeV interval, the lighter regions was then 3 or 4 GeV and so on. And red and orange tones are excluded in the sense that here the global minimum is charge color breaking. The blue points are those where the global minimum is indeed the electroweak minimum. Now, if you want to do a conservative estimate and say, okay, we are only interested in parameter points where the global minimum is the electroweak, we have to start here, for this case, at SUSY masses of above 2 TeV for a mu value of 350. Now, if we increase mu in the same manner as we increase MSUSY, this looks even a bit worse. I mean, this band in the middle is shrinked. You have to go to much larger SUSY values. However, and now I, of course, also used fine Higgs to produce a similar plot. One comment, this white bands here is again the issue where there are tachyonic bottom quarks in the spectrum. I don't understand quite why Spheno didn't find this. This is just for curiosity. So now here I have a mu of 500 GeV, and it looks quite desperate. So this the area where the electroweak vacuum is the true vacuum of the theory is opening at very large SUSY masses. However, this was for positive mu. Now we know xt is defined as AT minus mu. What if you go to negative mu value? Suddenly, a new area opens up for small SUSY masses. So this was a quite interesting observation. I would say that there you can go to this large values of xt over in SUSY and still find absolutely stable region for rather low SUSY masses. Okay. Now, as I said so far, this was only a discussion about absolute stability, the global minimum of the theory, nothing about metastability, quantum tunneling, the lifetime of the electroweak vacuum, smaller or larger than the age of the universe. Now, we want to discuss basically if we can rescue parameter points by the argument they didn't decay so far. Why are we not allowed to live in there? So to get basically the result on this vacuum tunneling, we have to go back to the 70s to this famous paper of Sidney Coleman, where he derived the decay probability per unit volume. This is how it was defined in this exponential way. So there is a coefficient a, and then the exponent of minus b, where b is the so-called bounce action, which describes basically the dynamics of this bubble wall that expands, and you can somehow imagine it like a pot of boiling water where there are bubbles of vapor expanding, and then at the end, when the water is evaporated, basically you are in the new vacuum state. Now, traditionally, it is said for a bounce action of B larger than around 400, the lifetime of the false vacuum is longer than the age of the universe. That means these points are certainly to be accepted. However, the B value crucially depends on the field space, and especially in this multi-field spaces. To use this calculation by Coleman, you have to do again a reduction to a single field space. And this is all independent of the SUSY parameter choice. So for one parameter point in the MSSM, you can get different answers by choosing different tunneling paths. This is one issue. The other issue is that we have a multiscalar theory. We have also a theory that has multiple different and maybe equivalent vacua that have different lifetimes. When you go from the electroweak vacuum to one of the several vacua, you have to make sure that, for example, you go to those vacua that have the shorter lifetime and not give a statement like from the tunneling only to the global minimum. This is also very important and crucial, and I'm going to show nice plots that we generated for this. So here, just one issue to show this variability of the bounds. This, so the decay probability depends on a prefactor that cannot be calculated. It is usually estimated by the scale of the theory that we denoted here with m. And now, if we vary this scale from 10 GeV to 100 TeV, we get several values, different values for this bounce action. And the color code is the following: that the more red points are those where the decay time is much smaller than the age of the universe. The green ones are those where it is much larger than the age of the universe. Let's say if it's 100 times the age of the universe, we don't really care if the vacuum is metastable or not. If we should have this decayed already 100 million years ago, we would be a bit more worried, for example. And then we can derive a 5 sigma survival and decay probability. And later we will consider this band between 390 and somehow 440 in the bounce action as an error estimate on the transition between long-lived and short-lived vacua. So this will be also important, or not so much important, but at least interesting later to understand the boundary between short and long. So now we want to go from this multi-dimensional field space to one-dimensional field space. In general, we have an n-scalar potential that looks like looks like this. This includes up to 3 to the n stationary points. This is a lot. And we put in an initial vacuum that is denoted here by this phi v, in the sense that, of course, the first derivative at this point vanishes. So this is the initial vacuum. Then we are expanding around the vacuum. Now we change the notation to a curly phi. And at the end, we define a unit vector and the length, where the unit vector basically points towards the interesting region in the field space, points towards the new vacuum, and the length is then given, of course, by the usual vector length. And again, we have a quartic potential where now the self-coupling, the trilinear coupling, the masses depend on the choice of the direction in the field space. This is a bit easier to deal with than the method I had before. And now that we have a one field quartic potential, we can go back to the literature, again to the 90s, and find a paper by Adams, where he semi-analytically got a result for a quartic potential bounce action that is given by this expression. So this value delta is basically encoding the coefficients in the potential, and then there are some numbers appearing here that come from numerical evaluation. What is now the big advantage by using such a pocket calculator formula? You can easily implement it, and you don't need to do any numerical integration for in the derivation of this bounce action. This is super fast, and certainly not so bad. And that's why we at the end decided to implement this number for the bounce, where you simply can feed in the parameters of the potential, and then you get a number, and you get easily your constraint on the tunneling time. However, still we are limited by the number of fields we can include, since the problem grows exponentially with the number of fields. At the end, we had to stop using 6 different field directions because for more it simply took too long. And especially in the MSSM, when you now want to include all this, how many was it, 18, 20 new directions, you simply cannot do it, also not numerically. However, you can go to a certain subset and then say, of course, the down type and up type neutral Higgses we always need. We want the top squarks, we want the bottom squarks. We can also include the tau sleptons, and then choose either top squarks and tau sleptons or bottom squarks and tau sleptons. However, all the sets you have to run independently and then basically compare at the end the results if you find more short-lived vacuum in the other field set. The electroweak vacuum, of course, is given by the usual electroweak VEF and the angle beta. And here we are also considering only real fields and no spontaneous CP violation, which makes the problem even more complicated. Now comes the application to the famous benchmark, SUSY benchmark scenario paper of our host and his collaborators from 2018. We chose some of these benchmark points to do our own vacuum stability analysis, and of course the most interesting one is this M(h)125, where the parameters are given here. xt has a value of 2.8, TeV, all the A terms were set equal. And then let me show first this benchmark claim from this paper. There was discussed basically experimental and theoretical constraints on MA and tangent beta for this scenario. Here in green, we have a standard model like Higgs mass, so the 125 line is there, for example. In blue are direct exclusions from A to tau tau. And this hatched, what is this orange or red hatched and this gray hatched regions are exclusions from, I think, Higgs bound Higgs signal, something like this. Maybe Sven can say.
The vertical, nearly vertical line comes from the properties of the standard model like Higgs boson.
Yeah,
so to the left, they're not sufficiently standard model like. And below 122, the light Higgs boson mass simply comes out too light.
This makes sense. Now we, for our analysis, we chose a point that is, of course, not excluded, in the sense that we are somehow in this edge close to the 125. So we say whatever MA 1500 and tangent beta say 20. This is that black cross that appears now in the same plane. And now we simply characterize the vacua. So we do our numerical minimization. We look into the lifetime. The dark green indicates fully stable vacua. That means the electroweak vacuum is the true minimum of the theory. The light green are long-lived in the sense that they are metastable, but the lifetime is much longer than the age of the universe. And the red and orange, which is the small strip down there, they correspond to short-lived vacua and somehow in this intermediate region, which are these few dots at the end of the thread, strip down there. So for this benchmark scenario, I would say we don't really have to care about short-lived vacua because they are anyways in the excluded area. However, what I personally also find interesting, that the experimental constraints somehow follow this line and keep the stable area open. So even the metastable long-lived area is already excluded by experiment. I mean, this is just a nice observation. If there's something behind, I don't know. If it hints towards us living in a stable and not a metastable vacuum, who knows? Now we classified the global minimum here on the right side. The global minimum is basically determined by Higgs and spot wefs in blue. The Higgs and stop wefs are only the small yellow edge here. And the so-called most dangerous minimum we show here. So there we have this lower left corner is indeed a case where the stop wefs are important in the sense that the tunneling from the electroweak vacuum to the minimum that has Higgs and stop wefs is shorter than the tunneling to the global minimum. And this is important if you want really to get a quantitative statement on the lifetime of the electroweak vacuum. Now, if you say, I'm only interested in the tunneling to the global vacuum, you miss this part, and then maybe you get the wrong statement. So finding this most dangerous minimum is quite important. But since we have a fast machinery, a fast numeric procedure, we can easily derive the tunneling times and define the most dangerous minimum, which is going to be shown on the next slide. So now we started in this benchmark plane, MA over tangent beta. We selected one point, and now we want to swap the parameter plane and go to A top versus mu. Again, we keep A top equals to A bottom equal to A top. This is varied, mu is varied. This dashed line indicates the original benchmark plane of xt equal to 2.8 TeV. This black cross is the point we selected. And surprisingly, this point is very close to the edge between long-lived and stable. So before we were in the middle of a stable region in the MA tangent beta plane. Now we swap the planes and we are suddenly at the corner. In red, again, are the short-lived vacua. This orange, yellow band shows basically this intermediate region where the bounce action is somehow in this error band that we estimated before. So again, the most dangerous minimum in most cases of this plane is actually driven by the Higgs and stopwaves, and the global minimum landscape looks a bit more interesting. There are now suddenly also stop and star waves appearing, but at the end, this doesn't matter because this so-called most dangerous minimum is the important one. Good. This shows now a line. So this shows all minima along this dashed line for the constant xt when we vary mu. The gray line corresponds to only the Higgs facts. This is basically the electroweak vacuum. And then we have all the new vacua that appear here. We have Higgs and stopwaves, Higgs bottom, Higgs star, and all the mixed in green, purple, and orange. Now the so-called most dangerous minimum, which is that minimum which has the shortest tunneling time, is indicated by this dashed line. Now we go along this line. In the beginning, we are in the Higgs bottom wave, and then suddenly we jump to the Higgs stop. So now if we would continue basically only considering tunneling into the Higgs bottom wave, we would certainly make a mistake. And the same on the other side here, we are first in the Higgs bottom and then we jump to the Higgs stop. But this is included for free basically in the analysis, because getting the lifetime of all this vacua is for free, because this pocket calculator formula is so fast. Now we want to compare our numerical constraints to constraints that exist in the literature. So one is this famous constraint of absolute stability, which has here the factor 3. And then also in the 90s by Kusenko et al. Was derived this first metastability bound where you get a different numerical prefactor here. So this was basically related to this metastability estimate. Furthermore, as what has been used in the literature is this so-called heuristic bound, where you just take minima and maxima of the employed parameters, build the ratio, and then you estimate it. I mean, make a rule of thumb estimate if this is larger or smaller than 3, and you get an easy and an easy to implement constraint. So now comes the comparison. The colors are the same as before in the same benchmark point. The black crosses again are selected. Point in the black continuous line is the stable constraint by Casas and friends. The dashed line is the long-lived metastability bound by Kusenko and friends. And this dotted box is this heuristic bound. Somehow they are all not so bad, and they basically show quite nice the correspondence to the result from this full numerical minimization of the potential, including all the 6 fields, compared to the estimate in only 1 field direction. I mean, this is quite impressive that this semi-analytic bounds are actually not so wrong. They are a bit wrong, as you see here, for example. There is this nose that is not covered by this long-lived bound. So if you say you only take here this lower line 7.5, and then you are at small mu values, but at large AT, you would say, okay, we are still long-lived. Also, the truth is we are very short. The same when you go for the heuristic bound into these edges, you would also make a mistake. On the other hand, if you say you take the long-lived bound and you go for small a values to larger mu values, you would exclude areas that are actually not excluded. So if you want to get a good statement on the quality of your bounds, taking the simple pocket calculator bounds might not be the optimal. Instead, the recommendation would be really to use a tool that does this numerical minimization and that does all this approximation of the tunneling time in a very short time that you can easily include into your parameter scans. So now why am I talking the whole time about a new computer tool? Also, there is already one on the market called Vivescius that does exactly this. And Vivescius uses for the estimate for this quantum tunneling another code called Cosmos transitions. This has the advantage that it doesn't use the straight line approximation from the electroweak minimum to the new minimum you want to tunnel, but it does some path deformation, and it also includes some thermal corrections that are important when you want to use the one loop results. Now we compare our analysis to the Vivescius analysis and the Vivescius one loop. So our analysis is pure tree level. Vivescius can include one loop. One thing that comes, of course, to the eye, that catches the eye, is there are here many white points. These are those points where Vivescius simply crashed. There didn't produce any result. This comes from the quite complicated setup to include all these loop corrections that makes it not easy. However, if you compare, let's say Vivescius tree level, Vivescius one loop, you don't really gain much by including the one loop corrections when you are purely interested in a constraint in the parameters. Of course, you may get a different statement if the tunneling in this metastable area is 100 times the age of the universe or 102 maybe, but at the end you don't care because it's still long enough. There were also some issues like here in this corners in this Vivescius tree level up and down on the right side, where Vivescius used the wrong minimum to tunnel in. I think this was like the case where they simply go to the global minimum, and then you find out, okay, when you define our most dangerous minimum, you do a better job. Okay. Now I can discuss some more scenarios that are, of course, from the setup different. The results also look a bit different, but conceptually it is all more or less the same. You can again go into the benchmark plane, define regions of stability, metastability, instability, define this most dangerous minimum, and so on. And then you do it for another alignment scenario, and suddenly you see all is red. So this is basically would be excluded then from the vacuum analysis. And then you want to rescue it by going now into this one point, swap the parameter planes, and then you see, okay, we are sitting here in the super short-lived region. Now we try to go in a valley where we still get the right Higgs mass, and then maybe you can end up in a more long-lived area. But then, of course, you have to check whether or not the Higgs properties change too much when you go to these regions, and then the nice features of this alignment scenario are maybe lost. So what comes next? Okay, then again this plot on the most dangerous minimum. Now the big advertisement. This tool is called Evade. It was developed by Jonas Wittbrodt, and it's available from his GitLab account. It's a C++ 11 library, and so all this minima finding is done by this famous homotopy continuation. So there are two approaches implemented, this from 4PS and something called Bertini, which I have to say I never heard before. I found it on his webpage when I looked for these features. However, I want to mention that we are only doing a tree-level analysis, which, when you compare it to the existing one-loop tool for this parameter scans, doesn't really make a difference, besides the fact that the available one-loop tunneling calculations might be theoretically a bit inconsistent, and there's some work to be done. But you can implement new models. Of course, you can also print out all the lifetime of the minima you can get, and then you also find that maybe you have some degenerate minima, as you might have it in the MSSM, where the minima are related with this set3 symmetry, and then you find out that they have a different lifetime, and then you find your most dangerous minimum, and the analysis is done. Good, then I come to my short summary to finish just before 5. I discussed these constraints from vacuum stability, metastability in SUSY, and basically the main advertisement at the end is to provide access to a new, fast and numerically stable tool that is called evade. This can be used and implemented in future parameter scans. And one important comment I really want to make: the global minimum is not always the most dangerous one. So if you just compare the lifetime of the electroweak minimum tunneling to the global minimum, you do a mistake. However, this is all included in the scope. Nevertheless, we do a tree level, and it is sufficient when you are just interested in basically in the constraints in this parameter regions. There's not really much difference by using one loop tools, and also this one loop minimization of this Coleman-Weinberg potential is a bit tricky. And if the tree level analysis is stable and gives good results, why do you want to go to a more complicated setup that at the end simply cannot provide the numerical results as you wanted? So tree level is good enough. It finds the most dangerous one, and it's fast and stable. Thanks for listening. I'm happy for questions and discussion.
Yeah, thanks a lot, Wolfgang, for this. Well, I found it very interesting and also easy to follow, I have to say. Of course, MSSM I worked with for a long time, but I found it very clear. Thanks a lot. Before we come to other questions, is this the original text for this cartoon, or you made it up?
I did not make it up myself.
But somebody made it up.
Somebody made it up. And I'm not sure if it is the original text, but I have the feeling it is.
Okay, thanks. Good. Are there questions on the vacuum? I have several questions, but okay. I start at least with one question. Can you go back to slide 19, please?
19?
Yes, this one. Yeah. So when you were analyzing the MSSM before, you said that roughly xt, the absolute value of xt, should be smaller than MSUSY, or xt over MSUSY should be smaller than 1.
Here we have larger SUSY masses. I mean, this was in this before where I had.
It was for 1 TV, yeah. No, you have large.
Yeah, no, yeah, but there I don't. I mean, I have to look into the paper what was like tangent beta and all these things.
Mm-hmm. I was wondering, because there you really seem to find this limit, and here we are at the nearly maximum value of 2. I mean, where the dependence has the maximum. And I was wondering what is so fundamentally different there.
Yeah, this. I mean, as I said, I have to take a closer look into this previous paper. Basically, what. Where is, what the other parameters were, but I mean, here, of course, you did your sophisticated benchmark scenario that was tuned in a way that all the experimental constraints are certainly fulfulfed. In this analysis,
not yours, though. Yeah, we never looked at vacuum stability when
yes,
we were defining it.
Of course. I mean, this is why we did this. But in this previous thing here, I didn't look at all into experiments. Only I tried to fix this DX mass observation.
Okay.
So I don't know if basically these plots that I showed there before, if they are excluded when you take more constraints into account.
Okay, but if you find the answer, please let me know. I would be curious about it. And another question on, I think, page 21. Yeah. I was surprised that you find the global minimum from the Stau is steeper than from this bottom. I mean, you consider the third family only, I think, because of the Yukawa couplings, that they are larger and they play a larger role. Now, certainly the Yukawa coupling of the bottom is larger than the one from the tau. And therefore, I would naively assume if all the other parameters are the same, like the A parameters, and they are the same, then I would expect that the bottom gives you usually a stronger, larger, deeper minimum.
I mean, for this we have these plots that you can take a look here, and okay, so this is along this line, of course, not for the full for the full plane, but if you now take a look at this large negative value, this large negative values of mu, you see that the difference between the what is it? Blue is bottom Higgs,
and
orange is top Stau. I mean, the difference is not so much.
Yeah. I'm surprised about the fact at all that it's deeper. I believe you in numerical analysis, but I'm surprised.
I mean, I have to say, a bit more surprised why then this that has 3 waves is deeper than this that only has 2 waves, because especially the stop and Stau, they don't talk to each other.
Okay, I mean, a multidimensional analysis in this sense is always difficult to explain this kind of details. Yeah. Okay. Curious. Well, at least this is also something that I learned, that this is possible. Good. Are there further questions?
Can I ask a naive one?
Yes.
So you say that one loop corrections are not important. If you didn't have supersymmetry, they would be all important, because in the non-supersymmetric theory, the one loop effects are the ones that produce instability.
Yes.
So my question is, what happens if you now take these models and try to play these games of split supersymmetry, when you gradually make supersymmetry more?
Yeah. So I think then of course they play a role, and I think even in the MSSM, when you don't have split SUSY and you include the one loop running, you certainly would run into similar problems you have in the standard model, in the sense that you drive new minima at larger field values, and this, of course, we didn't include here yet. So I mean, then you really have to compare the tunneling time of these guys, basically the electroweak, to minima in the vicinity of the electroweak scale, to a new minimum that is derived from the pure one loop effects at, I don't know, 10 to the 10 GeV.
Okay.
But this certainly could be interesting. This is true. But what I wanted to say for this analysis, when you just look at around the SUSY scale, if you take the tree-level potential or this Coleman-Weinberg improved potential, this doesn't make much difference when you only want to want to find the constraints in the parameter.
Mm-hmm. Okay.
One more little thing on this one. It's a more technical question. If you walk along this line, you say you're in the benchmark scenario. And of course, this must then be a walk along tangent beta. Yeah. So what are the tangent beta values, if you know this, maybe, which are in the green region, in the two green regions? I mean, 20 is the cross, yeah, but how much does it go up and down? You know this? Of course, one can calculate it, but
but I'm not. I think we kept it. Can it be that? No.
No. Then you would.
No.
It must be tangent beta that fixes x. Well, you said the relation for xt is at minus mu over 10 beta. Okay, maybe I'll just look it up and figure it out myself. The calculation is super trivial, of course. Just curious. Okay. Don't worry. Maybe one final sentence for me to make you also happy. We were discussing the difference between the two codes, vivacious and evade, at DESY and also in the working group or in the project where I'm in, and we concluded that we will stick to evade because it seems more stable and more reliable.
Yes.
What you say?
Of course, when you have basically an in-house code, you would prefer to use this one.
Yes. Good. I don't see any other questions, despite the fact that you cited several times the work of some of my colleagues who are connected. Good. Then.
Okay, my comments. Let me.
Carlos. Yes.
No. I just wanted to. It was a very nice talk. Concerning these two codes, vivacious is still maintained or is not really?
To my knowledge, it is still maintained by one of these authors. I'm not sure where this Jose. Where did I refer to vivacious? Here. I think by this Camargo Molina. He is still in the field and he maintains it. And I think there was even a C++ version coming out that we discussed in the STACY group some time ago.
Yeah, the C++ version is out and it's the only one I think that is still maintained. Yeah.
Okay, yeah.
And why is much better, you said, Sven, I mean much better the other code, the one that you constructed?
Well, you can see it here in the three plots that Wolfgang was presenting. For example, there are regions where vivacious tells you incorrectly that you are metastable because it doesn't look for the most dangerous minimum, but only for the global minimum.
Yeah, so it makes certainly this mistake. And then I mean, of course, to say our code gives the nicer plot is not really an argument, but somehow I'm a bit skeptical when here at this border area there are some points suddenly red, green, and where you don't really know, and also here in between there are some red points popping up. This all looks like some numerical instabilities that you are suffering or you are facing in this code, where our code seems to be a bit more stable in this respect.
And the number of fields that you can use in both codes is similar, or
I think it's the same. Vivacious has this field sets implemented, and I think the maximum number was also 6, if I remember it correctly when I used it the last time.
What would you have to do if you want to go to larger numbers?
You have to wait more. I think you can do it. It's not really an issue, but it's not feasible anymore.
Okay. Maybe Carlos is thinking about his favorite new SSM, where there are many scalars.
Many more fields. No, but it's interesting to have these codes to check the points. Very nice.
Okay, good. Then Wolfgang, thanks a lot again. Yeah.
Yes, thanks for the
very
invitation.
interesting, very nice.
Was a
Yes.
pleasure.
And next time in 3D with tapas. Yeah. Good. Then we stop here.
Okay.
I stop
And
it.
yeah. Okay.